Hi, my name is Gabrielle Beck, and I am currently a PhD student at Johns Hopkins University. And today I'm going to be presenting to you all on work I've done with other collaborators at GHU regarding automating the development of chosen ciphertext attacks. So despite the fact that it's currently 2020, there are a lot of software systems that exist on the internet which are using unauthenticated encryption. This is particularly concerning, mostly because unauthenticated encryption is vulnerable to chosen ciphertext attacks. Cryptographers and these larger security community are aware of this being a problem. However, sometimes it's hard to get developers to choose to utilize systems which are secure against these CCA attacks. Sometimes this can be because of perceived efficiency concerns. Other times this can be because the software developers have already started implementing and they don't want to change their systems. Indeed, it usually seems to be the case that unless you have a proof of concept exploit, developers just aren't all that interested in patching because they can't see a direct negative consequence of continuing to do what they're currently doing. This is despite the fact that CCA attacks can be particularly devastating and practical. In fact, one of the most well-known examples of a CCA attack, Sergei Vodunay's on AES run in CBC mode, only takes a linear number of queries and access to a padding oracle in order to completely decrypt a target ciphertext message. And ever since his seminal work, we've seen attacks that have been done with other more diverse sets of oracles as well. So even if you patch for padding, for giving up padding oracles, if you don't check to make sure that you're not revealing to an adversary whether or not a message is validly compressed, or if it represents a correctly formatted XML document, you can still be vulnerable to these types of attacks. So overall, this state of affairs kind of puts cryptographers in a difficult position. That is, if they want to not see unauthenticated encryption in use, they have to actively come up with these attacks, and these attacks can take a long amount of time to actually implement. Mostly because not only do cryptographers need to understand the malleability of the underlying encryption scheme, they also need to understand how that interacts with the oracle that the software developer is exposing. And our main point with this work is to try and take that sort of onerous effort off of cryptographers. That is, we wanted to come up with a tool that would automatically do this for them so that they could hopefully focus on other things that are potentially more valuable than checking every single combination of insecure crypto with the oracle that the software developer is using, or well, more or less exposing. So in order for us to do this, we had to first think about how a human attacker approaches a CCA style attack. Typically, what a human attacker does is they gain access somehow to a target ciphertext C, perhaps seeing it passively over the wire somewhere, and then they also gain access to an oracle O. And what they do is they take that ciphertext C and then they mull it in some predictable fashion using a malleation function fs, which we characterize by a malleation string s, and then submit it to this oracle. What the oracle does is it decrypts the mulled message and then checks whether or not it checks whether or not the message is validly formatted. Now, when it does this, it gives that result back to the adversary, and the adversary is able to learn some information from this. Specifically, what the adversary typically learns is that the message that they have the encryption of could not have been equal to some particular value or set of values. So if we look back at our padding oracle example here, we can see that an adversary has access to a ciphertext C, which encrypts a message that ends with 030303. And what the adversary is doing here is mauling in the second ciphertext block position. And what this does is it produces a result from the oracle, which is a false. That is, after you do this mauling, the message is no longer valid. However, you can imagine that if the adversary had an encryption of a message ending in 01, doing this mauling would have resulted in the oracle still giving back a true response. So this experiment is valuable because the adversary learns that the message they have could not have ended in 01. Obviously, this is not enough to decrypt the entire message. However, you can imagine that over time, if the adversary continues to make more queries, they will eventually be able to get the plaintext, or they'll get to a point where they cannot maul the message in any way that it will produce a different response from the oracle. So from this, it's clear that the name of the game is, for a human attacker at least, is to come up with really good malleation strings S. Mostly this is because the message space is exponentially sized. So, well, typically is. And so unless we're eliminating many messages from consideration as like candidate plaintext at once, this attack could take an exponential number of queries, which is not advisable and of course like not at all practical. And this is something that we're going to need to be able to emulate in any sort of automated tool. So it's something we should keep in mind. However, before we even discuss coming up with optimal malleation strings S, we have to first be able to come up with any malleation string S at all in an automated fashion. And how we're able to do that is basically by phrasing it as a SAT problem. And so what we mean explicitly is that we're looking at a SAT formula that's over Boolean variables representing our malleation string S and two validly formatted messages within our candidate plaintext space. And at a high level, what this formula is asking is, does there exist a malleation string S that whenever we use it to maul one of the message produces a true from the oracle, but if we use that same string to maul another message, it produces false. And assuming that such an assignment does exist, we can use a SAT solver to find S and then maul our ciphertext and then submit it to some target system that actually exists on the internet to get back a response, which will take out candidate plaintext. However, as I've described this, the SAT formula only ensures that our malleation string is valid. It could be completely arbitrary. That is, there's no real notion of a good malleation string S, which cuts out a lot of messages. So instead of phrasing this as a SAT formula, we choose to phrase it as a max sharp SAT problem, which essentially allows us to say, find me the malleation string S such that the number of messages that produce false is large and the number of messages that produce true is also large. And so essentially what we're doing is we're no longer talking about individual messages, but actually like sets or classes of messages. And essentially what we're looking for are those malleation strings S, which cut the candidate plaintext space as close to half as possible at every single query that we make. And luckily for us, such a max sharp SAT oracle, which I've previously described, can be implemented in software, even if it is difficult to do so in practice. As you can see from what I've just described, the attack that we're running is essentially greedy. That is, we're trying to eliminate as many messages at every single query. You can imagine that for some format functions, this is actually suboptimal. However, for what we've tested against, it is relatively effective. And perhaps more importantly, the results are easily interpretable by a human being and can actually be a stand-in for a proof of concept exploit. And so it's this exact algorithm which we've implemented in Delphinium. So the only thing that Delphinium requires from an end user, well, the number of things that Delphinium requires include a description of a malleation function, FS, a description of a format oracle, and then access to some target system. And given these things, if you can give Delphinium an encrypted message, if it's possible for that message to be decrypted entirely using a CCA style attack, Delphinium will do so. So once we came up with this tool, we wanted to test it against a variety of different things. So we implemented many different malleation functions and format functions, and then ran Delphinium against different combinations of these things. We looked specifically at profitability, time, and total query count, where profitability here basically means how good was our string ass. And we give this information within Delphinium directly to the end user. So some of the format functions we tested against include PKCS7, session tickets, and then a subset of ARM instructions, specifically the thumb ISA. The full results are available on our ePrint, and we would suggest anyone that wants to look further into this to go there, as it has our most up-to-date results. In the future, we'd like to see Delphinium used in the wild, that is on services that are actually running on the internet. So if anyone has any suggestion for targets, we would be happy to collaborate with you. Please talk with us. We also want to look at different kinds of oracles, specifically those that give up side channel information, and to extend our work to more complex format functions. Lastly, we would like to thank everyone within the SAT community who has helped us, along with those who have provided computational resources. We appreciate your help. Thanks for coming to this talk. If you have any questions, we would be happy to take them.